Hi everybody, this video is so that we can understand potential energy diagrams, and we're going to use a new table from the reference table, table I. Alright, so we're going to start off right here, potential energy diagrams, and you already know potential energy means stored. These show the changes in the potential energy of the reactants and the products. As a reaction is going on. So we're going to start off over here, with our first reaction being a dynamite explosion. So the first thing I want you to do is draw a nice axis here. We're going to have a lot of things that we label along the way, so make sure that you really use all of your space. Alright, I want you to think about dynamite for a minute. Dynamite has an incredible amount of potential at the start, so I want to start pretty high over here. This axis is representing potential energy, and a reaction occurs over time, so I want to have time here. Alright, so here's my reaction. I'm starting off with a lot of energy in my reactants. And even though dynamite has a lot of energy, you don't get an explosion unless you add a little bit more energy, that spark, that flame that you're adding to it. That's called activation energy, the energy you add to get something going. So we are going to go up like this. That's our activation energy going in. And then you know when it explodes, a lot of energy is released. And then the ashes have much less energy compared to the products. So we need to do some labeling now. Let me get a different color here. All right, from here to here up, this is the potential energy of my reactants. And over here, this is the potential energy, I should have made that big, but potential energy of the products. Alright, so those are pretty easy because what do you have at the start, what do you have at the end, and this is how much energy is. And I could actually have little values here. We could say that it started with 100 joules of energy and it ended with 20 joules of energy, so there was a lot more energy in the reactants than there was in the products. Now if you remember this value, I'm going to make a little dotted line here, from here to the top, so just this little section here, this is my activation energy. And again, activation is what you need to get started. So in order for the reaction to start, it had to go from 100, let's say that it went up here to 130. My activation energy would be equal to 30 joules if that was my value over here for each of these. We'll say my potential energy in joules. Okay, lastly, I need the difference between where I started and where I ended. This is called the heat of the reaction. The heat of the reaction is delta H, the change in heat. That is always going to be equal to the heat of the products minus the heat of the reactants. So let's solve it for this reaction. My products had 20. My reactants had 100. So delta H is equal to negative 80. Anytime you have a negative, you have an exothermic reaction. So I know we've used this word before. Exo, you are reminded that the energy is coming out of the reaction. This huge downslope is reminding you that energy is being released. So here you are, a lot of reactants, not a lot of reactants, a lot of energy in the reactants, a little bit of energy to get it going, and then a lot of energy released. And then to figure out how much energy is actually released from reactant to product, you do your little dotted line and you subtract. If the value is negative, it is an exothermic reaction. All right, let's try another. Go down here. This time, baking a cake. So I've got my time. I've got my potential energy. And when I talk about baking a cake, the ingredients have very little energy at the start. So here's my flour and my sugar and my water and my eggs and stuff like that. And it requires a lot of heat going in to bake that cake. But then the cake itself has more energy than the reactants did. So we will again fill in all of this. This here, what I have at the start, is the energy of my reactants, and here is the energy of the products. And again, you can call it potential energy or energy. It's the stored energy in a molecule. The amount that you need to get from here to here, hopefully you're saying all of these out loud as you're going. This is the activation energy. And the difference between where you started and where you ended, this is the delta H. We'll give some values. We'll say this one starts at 20, and we'll say this top peak is 50, and we'll say this one across right here is 40, just to keep our numbers nice and simple. So that means the energy of the reactants is 10, the energy of the products is 40. The activation energy is 50 minus 10, so that is also 40. And my delta H, 40 minus 10, that's a positive 30. When you have a positive value, you have this big uphill. Positive reminds you energy is going in. So this is an endothermic reaction. All right, always remember you can pause, you can go back, you can practice it, you can draw more diagrams to make sure that you understand each of these parts. Something that I didn't mention, there is also a name for this. At the very peak, if I go like this is what I call my activated complex. That's a great thing to know. Let me actually do a couple more things on here to show you. Let me use another color. I'm going to use green. If I was going to do this reaction in reverse, this would be my reactant and this would be my product. And instead of being endothermic, it would be exothermic, and I would go this direction. So the activation energy of the reverse reaction would be right here. Activation energy reverse. All right, what else do I want to add in here? A catalyst. All right, so a catalyst is something that speeds up a reaction, and I'm going to use the red to show it. So a catalyst does not alter your original energy. The reactants always have the same energy, even if you add a catalyst in. So you have the same dots, and you have this same all the way up. But the difference here is in the activation energy. It doesn't have to go as high to get started. It provides an alternate pathway for the reaction, so the reaction is more likely to occur. So I am going to get product a lot sooner, and my activation energy would only go to here instead. So the activation energy is less. So 40 minus 10, now my activation energy is only 30. And again, the time period, I have product here versus with the other reaction, I didn't have product until this time. So again, a catalyst is something like an enzyme, speeds up the rate of the reaction by increasing the likelihood of a collision between your reactants, brings them together. So it just brings that effective collision happening faster. If it happens faster, you don't have to add as much activation energy to get it started. All right, let's move along here. Next part, using table I. So here's table I on your reference table. We're going to go over how to use it. The first thing is it gives you the heats of reactions for several common chemical reactions. Of course, there's tons that aren't on there, but any that you would be asked on the Regents exam are on there for you. The heat of the reaction, delta H, is the difference between the potential energy of the reactants and the products. And I want you to make that little formula right here. Delta H is equal to the heat of the products minus the heat of the reactants. It's always got to be the product minus the reactant. That way you can calculate if it's truly a negative or a positive. If the heat of the reaction is negative, then the reaction is exothermic. This means that heat is a product, so heat is being released in the reaction. The reactants therefore have greater energy than the products. So you start off really high and you add a little bit, and then your products have very little energy. So heat is being released out right here. That's why you see the big downhill. Think of it this way. If this is our reaction, so let me go over to the next page here. A plus B equals C plus D. A and B are our reactants, and C and D are our products. Since we know energy cannot be created, gained, or destroyed, the amount of energy on both sides has to be equal. If D is heat given off in the reaction, so I'm going to write heat right here by this one, we know the reaction A plus B equals C plus D. A and B have more energy than C alone. So if these two actually have more energy than this, heat had to be released in the process. All right. If you consider another reaction, if it's endothermic, where do you think I'm going to put the heat? It's got to go on the reactant side. Endo means in, so it's got to be going in. It's got to either be E or F. So if F represents the energy needed for this reaction to occur, so F is going to be the heat going in, this reaction would have a positive delta H, and E must therefore have less energy than the sum of the products D and H. So E would have to get added to F in order to equal G and H. So that's why I know E alone would be less energy. All right, now use table I and look up reactions and determine if the reaction is endo or exothermic. So I grabbed table I, and there are all of these equations, and right across from it is delta H in kilojoules. So I'm going to find H2 plus I2. All right, let's see, where are you? It looks like it's way down here, like 3/4 of the way down the paper, and it says that it is positive 53. So if it's positive, this is an endothermic reaction. All right, let me find the next one. A lot of these look pretty similar, so make sure you find the right one when you're doing it. H plus OH minus makes water. It's the very last one on here. It says that it is negative 55.8. So if it's negative, this is an exothermic reaction. All right, and then we got this sugar one, C6H12 plus 6 oxygen. This is what we do when we are doing respiration, when we're breathing. This one's pretty close to the top. It's like 1/4 in. And this one is a negative 2804, which makes a lot of sense. We break down sugar and we take in oxygen so that we can fully break down the sugar, and we make carbon dioxide and water. The whole goal of respiration is to make as much energy as we can. This is what's going on in the mitochondria of cells. So because it is able to produce a lot of energy, that's because this reaction releases energy, so it's exothermic. All right, next thing here. Reactions in reverse. So when you go to look up a reaction on table I, if it's not present as it's written, but it is present in the reverse, then it's the same reaction, it's just the reverse reaction. It means the reaction is reversible. To get a heat of a reaction for a reverse reaction, keep the same number value, but change the sign. All right, so a negative becomes a positive and a positive becomes a negative. So if you remember when I showed you that curve, I said, hey, we could go the opposite direction, and instead of being endothermic, it would be exothermic. That's what you'd be doing if you found the reaction in reverse. So try these. Determine the heat of the reaction and if it's endo or exothermic. So 2 CO2s become C and O2. Okay, I actually think that a 2 does not go there. I think it's just CO2. Yeah, I found it. Cross off that. So CO2, this is again about 1/4 of the way down the paper. And the normal reaction is negative 393.5. So I'm going to change that to a positive 393.5. So therefore it is endothermic. All right, I find the next one. NO becomes N2 and O2. Oh, it's just a couple underneath that. And again, it's going in the reverse. So normally it's a positive 182.6. I'm going to make it a negative 182.6. And if it's negative, it is exothermic. It's releasing heat. All right, let's go down here. Change the amount of the reactant. So what if you had double the amount of reactants? Think about food. Heat energy could be the calories you eat. You eat one special K bar and you've got 100 calories of energy. Eat 2 bars, what happens? You've got 200 calories. So same is true for these reactions. Change the amount of reactants or products and you change the heat of the reaction accordingly. So try these, determine the heat of reaction if it's endo or exothermic. So I'm looking for NH4Cl, and again, I might see it in the forward reaction, I might see it in the reverse. All right, it looks like it's way down here towards the bottom of the page. NH4Cl becomes NH4 and Cl, and these all have 2's, which means it's double the value. So instead of plus 14.78, let's see, that would be, I could use a calculator right now, I don't have one, so 29.56, I hope that's right. I hope I'm giving you the right answer. I think that's what you get if you double it. And it's still going in the forward reaction, so it was positive. So endothermic. All right, let's do another one here. C2, actually, you know what? I'm going to skip one so that you guys have some to do in the end. So next part here. So put a little star here, come back to this, do this one without me. Positive values on table I indicate that the reaction is, okay, actually these conclusions, I want you to do these too. So all of these are things that we talked about and you should be able to make those conclusions on your own. All right, next page. Oh. Okay, drawing a potential energy diagram after using table I. So I want to find H2 plus I2 making HI. So H2 and I2, all right, it's about, again, almost 3/4 of the way down, and it's a positive 53. That means if it's positive, it's got to be added in as a reactant, so I'm going to add it over here on the reactant side. That means when I do, oh, that is so messy, sorry. When I do my potential energy diagram, I am going to do an endothermic reaction. So I'm going to go like this, and I'm going to go up, and I'm going to go here. So to make my numbers easy, I'm going to say this is a 10, and I want the heat of the reaction, which means the difference between where I start and where I end. I want that to be 53. So this means this number needs to be 63. So my delta H equals positive 53. All right, I don't know what the activation energy for this is. I just know it would go higher than the actual product amount. And that's really all I need to show on there. If you want to practice, you can label away. This would be the energy of my reactants, and you can go through and label your activation energy and the energy of the products. All right, I want you to do this next one on your own, so I'm going to put a little dot there so you come back and practice. All right, and then I've come to the end. This next part, you are going to, once you do your practice ones, check the key. Then there are hot and cold packs, and they are up in the front of the room, and you just have to find the right bags. Only add just a little bit of water and then hold the baggie so that you are breaking up the solute with your fingers, and that way you will feel it through the bag, and you'll feel if it's getting cold or if it's getting hot. And if it's getting hot, I want you to think about what type of reaction is producing this heat, and if it's getting cold, it's taking energy from the surrounding environment, like from your fingers and from the air. So I want you to think about what kind of reaction that would be and answer the questions. I also have lots of practice sheets, and this is definitely something that you're going to have to practice over time. So my expectations are that you will be able to draw potential energy diagrams and label them. You will be able to find reactions using table I and determine both the heat of the reaction and if it's endo or exothermic. Make sure you come in and see me if there is something that you do not understand. Thanks.